With that said, I was going to spend a tiny little bit of time going back talking about motor selection. And I've hinted at it a bunch of times, and so I don't think there's anything particularly new there, but I just wanted to kind of go through it. And one of the problems in the homework actually asks you, so which motor is going to go where and why, just to kind of go through it. So that should take about 5 or 10 minutes, and then I want to get into the details of the kinematics again. And they're related, obviously. But do you guys remember we talked initially about gear ratios on motors, which usually is a capital N, meaning the tau of the actuator is n times the tau of the motor, because you could put it through gearing, but as a result, the speed is 1/f of the motor, which also means if you look at the power, which is the product, right? The power of the actuator is the same as the power of the motor. A gear is just a gear, it doesn't add any power. But to kind of be clear on that, so if you've got some max speed and some max torque, one wants to say speed, one says omega, right? Then if I plot my omega versus tau, and these are my max values, it means my operating envelope kind of is anywhere in here, right? And if you add a gear ratio, then you basically shift this point, let's say down to here, and you can have kind of that workspace. Does that A make sense? B, the reason I bring up gear ratios, the different motors have different gear ratios. And so in particular, I'll draw it right underneath to be a little bit more clear. We have, I think, 3.14 radians per second, and half of that 1.57. And we have 4 Newton meter for the small motor. So the X5-4, where 4 is really the Newton meters, basically takes this spot. And there's an X5-9, which basically goes up to 9 Newton meter and about half that. So they're not exact the numbers. Obviously it should be the same. If this is half the speed, you should have twice the torque. So I don't know exactly why they don't fit quite perfectly. And then we have an X8 dash, I think it's called 8, though they say it has 9 Newton meters, which is this one. I'll get rid of that. And a 16 Newton meter, which is this one, right? So the X8 leads on a higher power curve than the X5 does. So one of the things that I'm going to ask you in the homework is to basically get, okay, of those 4 motors, which ones are you going to put where? And obviously the big ones are going to go at the bottom. And so do you guys agree that the calculation, if I have a mass hanging out here, so F is going to be mg, and I have some L, right? Do you agree that the tau of the motor, of the actuator I should say, consistent with my nomenclature, is just going to be L times F? And at the same time, the speed is going to be 1 over L times the velocity, if I put in the velocity here, right? So what we're going to ask you to do is basically estimate what the speeds might be that you want, but more importantly, what the masses are. And so the actuators weigh 300-400 grams. I put it in the homework, right? And you can basically add, okay, how many actuators are going to be out here, and add 50% to kind of say, okay, and the links and the screws and stuff. And then give me a rough idea of how much torque is going to be on this motor. And that should then be consistent with how many Newton meters do you have. And if you think about it, 10 newtons is 1 kilogram, right? 1 meter is probably the longest that I expect an arm to be. So a kilogram at 1 meter should be 10 Newton meters. So the biggest motor can do more than that, but that's basically the maximum. That's why I keep saying we're going to have a workspace and arms that are about human length. They're not going to be much bigger or stronger than that. As a side comment, if I put another motor in the middle, does that change anything down here? It doesn't change anything, right? Just because there's a motor in the middle, you still have to hold that weight. Obviously, this motor has the shorter distance that it has to do. Right? And so we'll ask you guys just to confirm, and then because we've got some selection of motors to kind of figure out which one's which. And as a random comment, notice this versus this. A length is effectively a gear ratio, right? It's a lever arm. So for the teams that want to get a really fast movement, if you want a fast V, basically, sorry, if I do that, right, you want long L's. So I mean, there's also a question of what your lever arm has to be in different places. And I'm not particularly looking at the the air hockey players, but maybe looking at the air hockey players that are talking about trying to get some faster motions in there, right? So we should think a little bit about what those lengths are going to be. And if you make it too small, it's going to be really hard to get speeds out of it. If you make it way too big, you're going to have too much inertia, and it's going to kill you too. So we'll have to kind of trade that off. And the final one I was going to make a quick comment on was the gripper, right? And so you guys realize the gripper basically, I think we've seen it at this point. There's a spool on a motor which runs a cable through the housing, right, that then pulls on, I don't know if I can draw this right, pulls on the fingers, and so that as you pull the spool, you collapse. So there's actually a rotation times that radius to a length change. Then that actually goes through a rack and pinion in here to move the fingers. That finger has a radius that actually closes it, so there's a whole bunch of steps between it. So what it means is that the L effective is about 40 centimeters. Meaning, if I want to grip at 10 newtons, I want to squeeze with 10 newtons, you're going to need a tau of about 4 newton meters, which, by the way, is kind of that guy. And the question is, how tightly are you going to want to squeeze? And so if you want to think about that, think about your fingers squeezing on an object, right? And you can stick anything in there that you want. Well, if there is an mg in the object, and there's a coefficient of friction, then obviously F has to be greater than the coefficient of friction to hold that. Well, how heavy an object are you going to want to pick up, right? And so 10 newtons seems like it's plenty strong to me, so just kind of to put that all over. Does that make sense? Is it getting boring? Yes?
How heavy are the heavies, just for, or what is that?
The X5s, I think, are 350 grams. The X8, I think, are 500 grams. I'm assuming that we're not going to fly the X8s out there, so I assume it's about 300 grams per motor. And so if you build a 3-dot wrist and you want to stick it a meter out there, you're looking at about 1 kilogram out there already. And so you're definitely going to want a big one on the base. Now that's a pretty massive arm to have 3 motors sticking out there at that distance. I'm assuming most people won't have 3 motors out there, and most people won't probably be at a full meter. They might be a little shorter. So we should be about in the right ballpark. But, please.
Is this like a peak torque spec? Do you know if that peak torque is like achievable for like a reasonable amount of time, like a second, or is it?
Yes.
Okay.
So you're peeking ahead, and here, I'll share it with the rest of the, I was going to show it in a moment, but you're ahead of me, which is A-okay. Basically, the motors generally have a continuous torque and a peak torque. Are you coming up? Hello. It is waking up. So this is their spec sheet. And so they've got a peak torque and continuous. And if you look at the X54s, it's a 4 Newton meter, and X59 is a 9 Newton continuous. So you can hold that forever. Problem is it heats up, right? That's what ultimately limits it. So for a brief moment in time, you can stick a lot more current in it and get more out. Usually that's on the order of a second or so. And so my comment is, if you want to hold a weight out there, you can't rely on it. If you want to hold the weight and then move it, Well, that motion is probably only going to be a fraction of a second or half a second. So you can probably use that peak to give you a burst of acceleration temporarily. So in these calculations, I tend not to worry so much about how quickly you're accelerating unless you're going completely nuts, like maybe our air hockey team. But anyway, sorry, I'm just picking on you guys because it's fun. But basically, I think of these calculations generally as continuous because you want to hold something, you don't want it to fall. And then the peak gives me a burst when I need it. It has built-in thermal models, so it actually looks at how much temperature is coming. It knows its own, and if you look at the housing, right, it has all the heat fins and everything on it. It knows the thermal time constants that it dissipates energy in, and so it's got a little model that it runs as to how hot it is. And so based on that, it will cut you off when it needs to. And you can actually, if you look at their status messages, you can see whether or not that caps in. But yes.
Will it tell you where it's going to cut you off? Does it report what it calculates its maximum to?
I think it actually, if you dig through it, I think it gives you the current temperature so you can tell how close it's getting.
So does it tell you, I will let you come in this much, or do you have to figure that out?
I think it is, I don't know, I have not tested it this. My guess is that it's abrupt, that it'll give you the continuous torque until it decides it's too hot and then it'll just take it away from you. So it won't ramp it down, it'll just suddenly take it away. Which is one of those reasons that it's just bad form to rely on it, right? I mean, if something's happening, that burst is nice, but otherwise you can't really rely on it ever being there because you don't know when it will be. And then just to finish that conversation, if you look at the X series gripper, right, so this is their picture, and this is the spool in the back pulling the cable. They put this other motor in here just to bolt on the gripper, and that spins the gripper. We don't necessarily need to put that motor there. That's just for people that want to spin the grip. It's kind of convenient. But basically, they give you just this, which is exactly that, which is if you want 10 Newton meters of grip force, you want X54. They give you a finger torque, which is the torque about the finger, which doesn't really tell me much. I really want the squeeze force. And so that's the table that basically confirms that calculation. So, with that said, questions on that? And so I'm hoping at this point people feel comfortable with how they're going to build their robot. We'll ask you kind of to go through the numbers, but I mean, by definition, the big ones are going to be in the bottom. And I just want to kind of confirm that we're in the right ballpark. That said, let me talk about 5 more minutes about SCARA and kind of the configurations that you can get. Because I mentioned it last week and we talked about it on Friday with teams. The reason a SCARA configuration, so these are robot configurations. So if I draw this, there's always a question of how to draw this. But basically, an original SCARA looks like this, where it has a up-down linear one in the back. And so it moves the first 2 motors kind of in the horizontal plane, and then actually the last motor goes straight up and down. And the reason they do that is exactly for that reason. So the big pro is that there's no gravity load, right, on J1 and J2. So what a lot of times it gets used for is if there's a pick and place operation, right? You hover over the table, you go down, grab it, move it, go down, grab it. So if you're working on a table, that's a lot of times a mechanism that people love doing. So it's great for kind of planar. It breaks down if you want to go 3D. Because it's really good at going up and down. It's really not very good at kind of going up there and going over there and stuff because of the way the joints are configured. And the other thing that's really annoying with it, it basically wants to go down. That usually means that this whole thing sits on a pedestal, right? Because it hovers over the table. So for what we're doing, it's actually kind of annoying in that you probably would want the motors to be hovering over the table so then you can reach down on the table. So that's kind of one drawback that it has. It is basically, it mounts up high. And the other drawback that it has is you're actually flying these motors fairly far away from the base. If you compare this to kind of the other option, which is you still put in your first motor vertically, but then, let's see, how do I draw this? Try to draw it in a way that makes sense. Basically, attached to that, a motor that kind of runs out that way. Right? And so now you're building an arm that can rotate around, but basically has two links this way. This motor is actually sitting in the shoulder. Right? So you have a lot more mass pulled inside, whereas with this kind of robot, you actually have more mass sitting out farther away. So this actually is good in that the inertia is kind of tighter, if that makes sense. And the big thing this is good at reaching over stuff, because kind of by definition, you kind of get this arc. And so if we're bolting stuff to the table, that's actually a big pro. So I just kind of wanted to go through that comparison. Those are kind of the basic two configurations that people do. And really it's just a matter of kind of, is this motor all in the horizontal plane, or is it kind of in the vertical plane? And there's pros and cons, right? There is no absolutely right solution. Does that make sense? So that means these you generally can mount more easily on the table and then reach up and over, which is probably something that suits our kind of configuration a little bit better. If you go all the way through, you could argue that there's also the ultimate answer, or the, not ultimate, but the final one, which is what happens if you actually put the first motor kind of on ground. Sorry, I'm not drawing this very nicely at all. And then kind of put, I don't know, a roll or something out here. So what happens if the first motor is basically directly in this plane, right? Then every motor sees the gravity loading. There's usually not a lot of reasons to do this, right? Because you might as well have your first motor not see gravity. The only slight thought I'll make to that is if I look at this guy, if you think about what it's doing is, if I come from the outside in, right? The outside is sweeping kind of in this plane, and then the base motor is rotating that plane around. So if I look at my workspace, do you agree that basically the outer joints kind of do this half moon, and then the base joint kind of causes this all to rotate around in this fashion? And you can kind of see the similarities are in that pole. Which means if I take this thing and I go straight above, then I can spin my bottom, but it doesn't actually move my point anymore, right? So this arm fundamentally doesn't like being straight up and down. That's its blind spot, its singularity. If you look at this arm, basically it is swinging the other way. So what you get, let me see if I can draw this one. How did I try to draw this? Is you basically get kind of a arc swinging this way, and kind of the singularity is now sticking out this axis, right? I mean, it's basically rotated from that one. So this one is much better, and this one actually, if you go straight up, is perfectly happy being straight up, because it doesn't have the singularity there. So part of this is kind of, well, where's your workspace? And a lot of times when we build a robot, you're going to reach over and grab something. Well, in that case, your workspace is probably kind of right out here, in which case that's totally fine. If you really want to reach straight up, you probably want this kind of a style. And if you think about it, if you reach straight up, the gravity loading is actually not that big a deal, right? The gravity loading is only a big deal if you reach out. So I feel like I'm spending too much time. I don't really want to go through, but there's all these kind of trade-offs that you can potentially make. And I know that we talked a fair amount about kind of SCARA and everything, so I just wanted to lay that out a little bit. So when I look at these, I think a little bit about where my singularities are, where my workspace is going to be, and kind of what that trade-off is. I think for most of us, we're going to reach over more than we're going to reach straight up, because the objects are going to be on the table, and we're going to be mounting the robot on the table. So this kind of scenario is usually the one that you want to pick. If you are going to be mostly in the plane, we can talk about kind of this, whether that makes sense. But that's kind of the options. Did I kill that topic? Other thoughts? Are people, I mean, it feels like most people are pretty clear about the way they're going to build their robot. If not, let's keep talking about it. But that's obviously the goal for the day, or for the week. And with that said, I want to go back to the kinematics. And here, before I turn this off, the reason I left it running is because I wanted to show one more thing. What I really want to do, are you going to wake up again? Come on, wake yourself up. So if I switch over to my virtual machine and run that command, which is in the homework, so don't worry about what it looked like. Basically, oh, that's bad. Yeah, no, that's good. Sorry. It just scaled really funny because of the projector. This is ARVIS, which is their visualization stuff. And so basically, I can turn off the robot model for a second. These are kind of the coordinate frames. These are the links, and you can kind of see them. Motors kind of sitting in there. And the nice thing, if I move this a little bit to the side, come on, virtual machine, be nice to me. Really? There. Whew. I also have these sliders. And guess what they do? Those are my motors. So if I grab the slider, I can move the robot around. And if I grab the up-down, I can move up, I can move down. And bring this one back into slightly better view. Go over there.
How'd you open the slider for the jumps?
So go through the homework, it'll tell you that. But basically, this is where I'm trying to go. And so we'll go through some of the math for it today, we'll go through some of the instructions are in the homework, and we'll go through some of that on Wednesday as well. But basically, kinematics is now saying, oh, I've got all these three motors, and I want to coordinate and get to that endpoint, right? And so this is their visualizer. And rather than taking the information from the actual motors, it is taking the information from this fake motor. This is just a fake motor, which is a slider. I could also take that information from a trajectory planner. So today I want to talk a lot about how to calculate this. But the reason I want to is because as of Wednesday or next week, kind of as we get to it, right? Obviously the goal is going to be, oh, I want this point to be over here. What do I need to do to my joints to calculate? I want to move there. Do I want to move in a straight line? What is the path I want to take, right? And so starting to do motion in 3D space and reorienting in space and solving all of those things and coordinating the joints is clearly what we need to do over the next few weeks. So this is the framework that I try to want to set up to that. So the homework should basically look like that. I'm going to ask you to effectively model, and you can do it graphically to whatever detail you want. I don't care about the graphics looking perfect at this point. But I'm going to ask you to model the kinematics for your project so you can see how it moves, and then we can basically simulate and observe kind of, and so as we start planning and playing with stuff, we'll be able to visualize it. And this is where I'm a big believer in plotting stuff, but if you give me a plot, I can't see the three-dimensionality of it, right? So this is a way to see the three-dimensionality of what's going on rather than just seeing a graph. All of that said, let me turn off my happy little guy here. Because I admit I'm going to try to do a little bit more math today. The reason I want to do it is there are built-in tools in ROS for all of this, but coordinating all the joints is kind of the bread and butter of robotics. If you can't figure out how to coordinate your joints, right, you're not going to be very good at doing robotics. So A, I want to do it because it's really the key to it. And I realize 133, is anyone taking 133? You guys take it last year? But it's not offered this year. And so did you guys go through all the kinematics and Jacobian matrix? Do you remember any of that? So I apologize, there will be a little bit of a review in some of this for you guys, but for a lot of people, I don't think you've seen that. And I also basically want to do it in a way that will let us customize it, because if you think about it, and we talked about it last time, every time you solve it, there's multiple branches you can do, right? Elbow up, elbow down, and so you need to understand all those things. Most solvers assume that you have a 6-duff arm. If you're only going to build a 5 or a 4-duff arm, you need to build something custom. And so we're basically going to have to write little custom solvers for our different arms. And so this is the kind of stuff that we need to get a handle on in order to be able to do the projects. So what I'm going to start with is the forward kinematics, right? Meaning you take your joint vector, which is an n vector, and basically calculate an fkin, x vector is an fkin of q vector if you want, to your tip, where that is both position in 3D and the orientation. There's the opposite, the ikin, the inverse kinematics, which basically says if I want to have a tip here, what do my joints need to be? We'll do that one kind of next week. So I'm going to stay away from the inverse kinematics because you can't solve both at once. I keep saying, oh, forward kinematics, fkin is my abbreviation for forward kinematics. It is basically a function. It's a one mapping. The nice thing is it's unique in this direction, which is why it's easier to start here. Orientation. We can do Euler angles. If it's not clear, I don't particularly care for Euler angles. They just cause mathematical issues. They're kind of nice, but they cause issues. We can do quaternions. I actually really like quaternions. But it turns out, for this kind of math, rotation matrices are actually the one to do. They are easier to understand, and they're actually faster to calculate because concatenating them is easier than concatenating quaternions. So we're basically going to do rotation matrices, and this is obviously just the vector 3D for position. Comment being that I'm going to do all of this in general, meaning I'm going to assume an orientation, full orientation. For a lot of the projects, you're not going to be able to reach a full orientation, right? And so what I want to do afterwards is actually not, you can go Euler angles, but basically go custom angles. If you only have 1 degree left on your wrist, well, might as well use that angle as your angle of your orientation, right? And so I'm going to derive it more generally, but then ultimately, I think we're going to go custom. So basically, the math and the algorithm to do that, which really means if this is L, you guys agree that I have L times cosine and L times sine Q is kind of my really stupid example, right? Which means I have to define an X, and I admit I generally define Z to be up, so I'll put my coordinate frame like that. You guys agree with that? So all I'm trying to do is basically do this in 6 degrees of freedom. First comment, what all assumptions have I made here? I used this as my reference, so I measured Q from here, right? If I had used this as my reference, I would have gotten a very different one. I would have gotten, what is that, minus L sine Q and L cosine Q. So I'm going to try to put these on the side. Rules, we need to define the zero position. For a robot. I've also, what's my direction of my Q? Do you guys agree that I've picked Q to be positive this way? So we also need to define our directions, our joint directions. being a little bit pedantic about this, but this is the kind of stuff, let's go through it carefully once, and then we should be able to do it. If I skip through this a little too quickly, I'm afraid that it's just going to cause chaos, and so bear with me even if this is being a little bit silly. Do you agree that I also effectively have put my coordinate frame right in the middle here? So origin, I placed the origin in the middle here. So we've got to define all of our coordinate frames. And I'm explicitly actually asking you in the homework is show me what your zero position is, what your frames are, and for your robot. Define it for your robot. Put it on a big sheet, nail it to the table, and use it as a reference, because from then on, that's kind of the definition that you've made. And it's arbitrary, you can define it, but once you have it defined, you got to stick to it. So, first comment, zero position is not the same thing as what I normally call home position. What's the difference? Just to be really clear.
I was going to say, like, the zero position is where all your coordinates are with respect to, but your home position might be the orientation of the robot that you want it to be in when it's not, like, particularly at target location or pose.
It's absolutely right. It is a kind of an arbitrary English language definition, but zero position, I mean, this is where my joint reads zero. There are sometimes systems where you can't actually get to zero. Right? And so normally you kind of start your robot up in a certain configuration in its sweet spot and it's nominal. So usually that I would call the home position. That's where it wants to live most of the time. That is not necessarily the same thing. Given that everything initializes at zero, a lot of times it's convenient to pick a zero position that happens to be basically where you want your robot to be, but it's also arbitrary. So let me do all of this. Let me do this on an example. So this is going to be a little bit of an involved example, but let's go through all the steps. So I'm going to pick a robot. I'm going to put its base joint kind of vertical, assuming that's what a lot of folks will do. Then I'm going to attach a frame to it, and then I'm going to stick another motor kind of on the side here. Is that making sense from a drawing perspective? So I'm thinking of this axis being kind of that way. Let me draw the axes in kind of being that way. Well, then I'm going to attach a link to it, and I'm going to attach another motor out here. And then, guess what? I'm going to attach another link out here, and just because I'm going to make it a Ford-off that has a gripper like that. So I'm doing a Ford-off robot. First one is about that one. The next two are parallel, and then because I feel like trying it, I put one out there like that. Does that make sense of what my robot looks like? So, A, you think that's a good zero position? I'm being a little bit silly here, right? Yay or nay on a good home at zero position? You're shaking your head. Why are you shaking your head?
It's the singularity.
You're starting a zero position right in the middle of the singularity, which is kind of, I mean, it means I can't move my gripper left or right, right? And so yes, mathematically I can define this to be zero, but it also, and it's going to work. You can always add joint offsets and just put the home position in a different place. But part of me is like, well, why are you doing that, right? And so I'm going to instead do, I should draw it the way it should, that. And pardon my terrible board technique, how's that for zero position? Right, so now the arm's kind of like this, which is much more logical of where you'd want to be. I mean, I could put it down on the table, but comment is you don't want it to be there. So you want the zero position to be kind of not singular, ideally in the workspace. And the third one that I was going to say is you want things to be orthogonal. again, none of these are hard requirements, but they're gonna make everything come out so much more easily, right? Because if all your rotations are 90 degrees to start with, the sines and cosines are much easier than if everything is at 38 degrees and you gotta carry these funny numbers with you. So, good with that? Step 2, joint directions. Well, the joint directions, I'm gonna argue, sorry, my board technique is getting bad. I was gonna make a list over here, except my list is getting ugly. The motors basically tell you which way they spin, right? They spin right-hand rule the way they're mounted. So which way do I have them mounted here? Well, I don't know. So I'm gonna right now pick them as being, okay, let me try to draw it in color so that maybe it's a little bit more obvious. I assume those two are the same way, and then I'm going to make this guy rotate that way. Right, so I've defined the direction that is a positive, and you know from the motor which way it goes that it's positive, right? So now we get to the good stuff, coordinate frames. Where do you want your world to be? How about I put my world frame X to the side, maybe a little shorter so it's more obvious, Y in, Z up. And I'm going to call that my world frame. Sound good? And again, it's arbitrary where you put it. So all of this is now going to be basically going from the world frame to motor 1, spinning around motor 1, going to motor 2, spinning around motor 2, going to motor 3, spinning around that one, spinning around that one. And so it is the kinematics of walking through that. So there is a lot of vector rotation math in here. So let me be, so I don't know why that ended up so far squished on the side. Nah, it is. Let me be really a little bit pedantic about this too, and define what I mean. And so we're going to use a rotation of I with respect to the world, which is going to be, right, the matrix of Ex I with respect to world, Ey vector with respect to the world I, and Ez vector with respect to the world. Do you buy that? Yes. What does world frame mean? At some point, I needed to define some reference, some ground truth. Because if I give you a vector, I'm going to give you 1.3, 2.4, and 7.9. Well, that's a distance from where? So I have to put an origin somewhere in the world. And the same thing is I've got to define what x, y, z somewhere in the world is. By usual notation, you tend to make z up. Roboticists like z up. Vision people tend to have z go forward and x, y up. Roboticists like z up. Convention. So basically, put a point on your table. Put a dot on it, and actually literally put a dot on it. I mean, actually, if you don't mind, put a piece of tape on it and then put a dot on it so that we can erase it more easily. But in some ways, at some point, you're going to put a block down or an object, and you're going to take out a ruler and say it is 30 centimeters from my origin, right? And then your algorithm better come up with 0.3 on the display to localize it. These are physical things we're now measuring. So place a real reference frame that you literally take the ruler relative and measure the distance from. That's my world frame. And so I'm going to define a rotation matrix as basically my x vector, my y vector, and my z vector. And I'm being slightly, I guess, pedantic, right? In saying it is frame I relative to the world frame. So expressed in coordinates, right? So this is in world coordinates, or you could say with respect to world, relative to world, whatever you want to call it. But I'm going to try to be good and actually note it, and I'm going to put it in the top left. Be kind of particular about this, especially for today as I'm going through the algorithm, because this is going to be relative to that, and that's going to be relative to this, and so if you're not careful, you get lost, and so I'm just going to be really overly picky. I'm going to define positions. And I'm going to say x is I to world expressed in coordinates of world. So what I mean is this is the vector. So if I put a frame I over here somewhere, right? That is the vector here relative to that. So it's this vector expressed in x and y and z in those three coordinates of the world frame. Does that make sense? Basically, it is generally implied that I is relative to w expressed in coordinates of w. So a lot of times people just write IF, do this, and they kind of, it is implied that it's relative to world. Or a lot of times people just write xi, and it is implied that it is relative to world. Right? And I'm betting in 2 weeks from now that's what we're going to do because it's just hideous to write all these things all the time. But I'm going to stick to the slightly snazzier, longer version for today, just to be clear. Does that make sense as to what I mean kind of by this notation? Anyone willing to admit not? Please. It is a vector from here to here. So this world frame has a location. So the length of this vector depends on that location. But now I could also arrange this world frame in different directions. Right? I could say z is up, or I could say z is to the right or anything. So one is saying I am looking at the vector from here to here. And the other one is saying I have a horizontal component and a vertical component. I could have made it a radial component and a or whatever, right? I could have changed my x, y, and z to be different things. And so this means it's the origin of the world frame that you're basing your vector off of. This means it is the axes of w that you're using to get your x, y, and z components of that vector. Right? Do you agree that if I rotate my coordinate frame and make my x and my y and z different, it's going to change the numbers, it's going to change my components, but the length of that vector is the same thing. And I hope this will actually become a little bit more clear as we kind of go through this. I'll actually tell you what, I'm going to redraw it over here just to have it a little bit easier access. And I'm going to make it. So I'm saying, and I said, I put my x, y, and z over here for the world. And I had this frame, and then I had my second motor sitting kind of here in that frame. And then I had a link, my third motor sitting up here. And then from there, I had this motor kind of, and that's meant to be kind of coming out of the plane, right? So when I draw it at 45, I mean coming out of the plane. Does that make sense? So, step one, we've defined our zero position, we've defined our reference, and now we need to go through and get all of our coordinate frames. So I've placed the world coordinate frame. Now what I'm going to do is I'm going to put a joint frame at each joint. But I'm going to do two things. I'm going to do a zero. Do you guys want to start numbering at 0 and start numbering at 1? 0 index, 1 index.
0.
It's arbitrary, right? So I'm going to call it joint. Fine, I'll call it I for a second, but then I'll start at 0. Right? I'm going to do a joint I minus, and so I'm going to have two frames. An I minus and an I plus. The I minus, I mean to be a frame that is fixed at the base of the motor, i.e. not spinning. Not spinning with motor I. And this one is the spinning frame with joint I. Meaning this one is fixed and this is the motor spinning on top of it. Does that make sense? So kind of by definition, these two frames are going to sit on the joint axis. Right? Because that's where the motor spins. So you put the frames on the axis and then one of the frames spins relative to the other one. Okay? So I'm going to place 0 minus and 0 plus. And where am I going to put them? I have to put them somewhere on this coordinate frame. So because I put this on the table, how about I put them right here? And I call this my x, y, z. And I say this is frame 0. Does that make sense? Do you see the blue okay? I'm going to put frame 0 over there. So do you buy that to get from W to 0 minus was a shift by, well, call it distance. No, I don't want to call it here, but we'll make, actually what, I'll use orange because I like orange. How about I call this distance A? I'm going to use A, B, C, D as my distances because I can't think of anything better. Do you agree that that is a plus A 0, 0 shift? And no rotation. Right? All I did is take this frame. Oops, I almost did this. Oh, so many times use your left hand. No, it's right hand. Right? Right hand. Shifted that over so that it lines up with this axis. Do you buy that to get from 0 minus to 0 plus was then just a rotation about the z-axis of magnitude q0? Because all I'm going to do now is spin in this direction, which was the positive z-axis. Yeah? So if I write that out, do you guys agree that x 0 minus relative to world was A0, 0, R0 minus relative to world, and I was already bad, I already said 0 minus relative to W is unity. Do you agree that x0 plus relative to world is the same thing? And R0 plus relative to world is now just RZ of Q0? Yes?
I guess these rotation matrices are not representing like absolute positions. They're like the deviation from.
So I am going to accumulate multiple relative rotations from here to here, from here to here to here. But in a collection, they will then be the absolute rotation relative to the world frame.
Sure.
So this one I meant here is a relative rotation. But given that you start with a unity rotation, that means this is actually my absolute rotation relative to world.
Okay.
Does that make sense? And just to put it up, I don't know if this is useful, but I will say RZ is actually CQ1, 0, 0, 0, sorry, C is cosine and S is sine, right? Let me go one more step, and then I'll generalize. Do you agree that now to go from 0 plus to 1 minus, I have to place the 1 minus and 1 plus frames? Well, kind of by definition, that frame has to be somewhere along that axis, right? What's the logical place to put it? I could put it over here, but it seems kind of silly. Seems might as well put it right smack in the middle there. So I'm going to put an x, y, z right here. And I'm going to say that is some distance b above the table. Agreed? So do you agree that the relative shift is 0, 0, b? Do you agree that the relative rotation, so let me actually be clear, x is x1 minus relative to O plus, and r is 1 minus relative to O plus. That rotation was unity. So guess what? That means I can now write, here, I'm going to erase this and write it out big. I can now write x1 minus relative to world is going to be x0 plus relative to world plus r 0 plus relative to world times x1 minus relative to 0 plus. Oh, yes. Do you agree that you start with the previous, you add the new shift in its relative coordinate frame? And guess what comes out of here? A0, 0 plus RZ of Q1 times 0, 0, B, which in this case turns out to be A0, B because RZ doesn't do anything to it. Right, and by the same token, R1 minus relative to world is R0 plus relative to world times R0 plus L1 minus, which in this case stays to be RZ of Q0. Agreed? So if I go from 1 minus to 1 plus, do you agree that there is no position change, because that's the whole point, I'm just spinning, and that the R1 plus relative to 1 minus in this case is an R, okay, what is it? We said we wanted this to be a rotation, I erased it, didn't I? Which way did I define it? I think I said this way. Do you agree that that is a rotation about the x-axis? Do you agree that it's the negative x-axis? Rx of minus Q1. So, is this getting hopefully boring enough? And I mean that in a good sense. If I generalize do you agree that I can propagate a position, as in the relative position gets in the right frame, added on to the previous one to the next one, and my reference frame itself is concatenated. Oops. Yep. So, rather than going through all the steps, does it make sense what I'm trying to do? I'm going from world to joint 1 without rotating, and then I'm rotating about, joint 0, and then I'm rotating about the joint. Then I move into joint 1 without rotating, and then I'm rotating, et cetera, et cetera, et cetera. So rather than write all these equations one at a time, do you agree that is the how to get from one to the next. So the only thing I'm going to do now is basically, excuse me, turn that into a giant, oh, I'm so sorry, we're actually running out of time here. What I want to do is basically, and how about we finish that on Wednesday then, is turn that into a table. That is basically going to be a table that says, okay, what is my x, my relative x? What is my relative r? From world to 0 minus, 0 minus to 0 plus, 0 plus to 1 minus, 1 minus to 1 plus, 1 plus to 2 minus, etc., right? And basically it is going to be a walk, rotate, walk, rotate, walk, rotate, walk, rotate. And that table will contain the lengths, right? And it will contain the rotations. And basically once you have that table, run a loop over it by those formulas. And that gets you out to the end. So I apologize in that I totally missed over time. How about we fill out that table on Wednesday and go through different scenarios of what can happen, et cetera, et cetera. But this, what I'm trying to do makes sense. This is being a little bit pedantic in walking through it, but getting those definitions to make sense and be self-consistent. Do it once, get it right, and then everything else will be quiet. If you try to rush through it, it'll just be a nightmare from then on. Sorry, there was a question that I... You are absolutely right. Thank you.
Good.